the last thing we saw was that f to the sum power for any permutation f is identity. You can always find some power such that it is identity. So now we get to define permutation groups. Definition: a permutation group of on X on X is a set G of permutations perms from X to X such that 1 for all f and g in G, for all f comma g inside G, and for all f and g in G, f compose G also belongs to G. Okay, which is to say G is closed under composition. G is closed under composition. Okay, and the second, I belongs to G. Okay, the identity should belong to G. We are not giving a formal definition of what a general group is, but what a group is, I'll quickly tell you, is a set such that there is an operation which it is closed under, and you should have the identity. And the third property is that for every element, the inverse should also be in the set, in the group. Okay, so lemma given a permutation group G on X, for every f belongs to G, f in G, f inverse also is in G. F inverse belongs to G, which is to say G is closed under multiplication, under inversion. G is closed under inversion. Okay, and so the three properties of a group are: first, it should be closed under some operation, which in this case is composition. Second, it should have the identity element, which is I. And the third, the inverse for every element should exist, which by this lemma does exist. How do we prove that? Relatively simple. Case 1. What the heck? Case 1. F is equal to I. Then f inverse, which is also equal to I, is already in G, and so it checks out. Okay, case 2, f is not equal to I. Then there exists some m such that f to the m is equal to identity, right? Therefore, f to the m minus 1, m, maybe let me say m greater than 0, such that f to the m minus 1 is equal to identity, and therefore f to the m minus 1 is equal to f inverse. Okay, and this belongs to G, as f to the m minus 1 belongs to G, right? And so it is closed under composition. So let us look at an example. Recall last time in the video I said that Sn is the set of all permutations, perms of X is equal to 1, 2, ... n, and then Sn is the permutation group on X. Permutation group on X. This group is called the symmetric group of order n, which is why we write Sn. The symmetric group of order n. Okay, so this is the first example of a group that we will be considering. The book also mentions something called the dihedral group. So let us try to write down what both of these are. Okay, so consider example 2. Consider regular oriented hexagon. Consider regular means all sides are same, or actually the standard way to write it is oriented regular n-gon. Okay, maybe 4, maybe 6. Let's take 6 n-gon P in the plane. In the plane. Okay, example n is equal to 6. So for n is equal to 6, I get a hexagon 3, 4, 5, 6. And what does oriented mean? So regular is every side is of the same length, all the angles are same. So it's a symmetric hexagon the way you normally see it. And oriented means all these edges have a direction. Okay, they go in a cyclic direction, they do not go in random directions. Okay, and let X is equal to the set of corner vertices of P. Set of corner vertices of P. Right? So then X is 1, 2, 3, 4, 5, and 6. Then it is easy to see that P has rotational symmetries. P has rotational symmetry. Symmetries, which is if we rotate P clockwise by some multiple of 60, if we rotate P by some multiple of 60 degrees, then whatever we get is going to look at the same figure, right? It's not going to look something different. It's going to exactly coincide with P. The result coincides with P. With P. Great. And every single rotation is a permutation of X. Every rotation is a permutation of X. Okay, and so what are the rotations and the permutations? Well, if I rotated M times, I'm going to write M here, perm of X, and name of permutation, name of perm. Well, the first permutation is I rotated 0 times. It's going to be 1, 2, 3, 4, 5, 6. Stays as 1, 2, 3, 4, 5, 6. Okay, and this is my identity permutation. If I rotate it once, then if I'm rotating in the direction of the arrows and I label them 1, 2, 3, 4, 5, 6 in the direction of the arrows, 4, 5, 6, then my permutation now becomes 2, 3, 4, 5, 6, 1. And this I'm going to call R. Okay. If I rotate it twice, the new permutation is going to be, well, I'm rotating it once more, 3, 4, 5, 6, or I can rotate it as moving 120 degrees, which is 2 vertices, 3, 4, 5, 6, 1, 2. And the thing is, this is just R squared, right? Or R composed R. I'm doing the same rotation twice, and 3 would then be 1, 2, 3, 4, 5, 6, goes to 4, 5, 6, 1, 2, 3. I'm not going to write every single one. I'm going to do dot, 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 1, 2, 3, 4, and 5. Actually, I could just write 4 and 5, whatever. Let me just write 4 and 5. There are only two left, which are 1, 2, 3, 4, 5, 6 goes to 5, 6, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6 goes to 6, 1, 2, 3, 4, 5. Right? This is R cube, R to the 4, R to the 5. And if I do it once more, I am going to get R to the 6. Note, R to the 6 would be the identity. Okay? So define, let G be the set of all rotational symmetries of P. G is equal to set of all rotational symmetries of P. Okay, which is then one identity R squared dot 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 R to the 5, right? And the order of G, as we saw above, is 6, right? Then 6 gives a permutation group on N, X, then, sorry, G, not 6. G gives a permutation group on X, and it is called the cyclic group of order 6. Cyclic group of order 6, which is denoted Cn. Okay, so C6 in this case. A cyclic group of order n is denoted Cn. A cyclic group of order 6 is denoted C6. What are their inverses? F inverse, identity remains identity. Inverse of R is R to the 5. Inverse of R squared is R to the 4. R cubed is R cubed. R to the 4 is R squared. R to the 5 is R, right? Because if we multiply them, if we compose them together, they are going to give me exactly R to the 6, which is identity. In general, the cyclic group of order n, the cyclic group of order n is equal to the group of rotational symmetries, the group of rotational symmetries of an oriented regular n-gon. Of an oriented regular n-gon. Okay. Now, what you can do is consider, instead of a regular n-gon, consider example consider a non-oriented regular n-gon. Okay, so instead of n is equal to 6, I'm going to look at now n is equal to 4. Example, n is equal to 4, and then it's a square, right, that we're all familiar with. But this time there are no arrows. All the sides are the same. Once again, let x is equal to vertices, which are set of vertices, which I'm going to say 1, 2, 3, 4 maybe, and so which is this is equal to just 1, 2, 3, 4. Okay, doesn't super matter as long as they're in a circular order. Again, we are going to have some rotational symmetries, but we also want to look at some other kinds of symmetries. P has rotational symmetries, but also reflectional symmetries. Reflectional symmetries. Okay, so what are the rotational symmetries? Rotational symmetries. Well, the same as previous time, I will have 4 rotational symmetries, right? I'm turning it by 90 degrees. 4 of the, not 6. 4 of these similar to previous example, right? By turning it 90 degrees instead of 60 degrees this time, I would be getting 4 rotational symmetries. And reflectional symmetries. Well, what are these? If we reflect the figure around some reflectional line of reflectional symmetry, then I get a new figure which coincides with P. If we reflect P along a line of reflectional symmetry, the result coincides with P. The result coincides with P. Okay, so for example, what are these lines of symmetry? Well, take a square, right? 1, 2, 3, 4, and take their midpoints and look at the line which passes through these two midpoints. I can reflect it around this line, right? It would send 1 to 2 and 3 to 4. Okay, that is going to be sends 1 to 2 and 3 to 4. So the image is going to look like image 2, 3, 1, 4. And now, howsoever many times you rotate this, this is not going to give you your original figure. Okay, so if I rotate it for 2 times something, if I rotate it 3 times in our normal direction, in clockwise direction, we will never get the original figure with the original vertex numbering. New amount of rotation will bring figure back to original vertex position. Okay, and that means this is a completely new rotational, this is a completely new reflection. Okay, this is a completely new, what is it called? Permutation. My bad. I just completely forgot. Okay, and so how many of these do I have? Okay, well, let us draw all of them. Lines of symmetry. Oops. Lines of symmetry. Permutation of X. And how it relates to the permutation. Okay, so you can check that you get this by composing these two. Okay, so the first one is this 1, 2, 3, 4. You're reflecting along this line, and this would make the permutation 1, 2, 3, 4 goes to 1 goes to 2, so 2, 1, 4, 3. And I am going to call this reflection as T. I'm calling my rotation as R, my reflection would be T. The next one is actually 1, 2, 3, 4. Okay, and what happens if I do this one? Well, 1 and 3 switch places. So 1 goes to 3, 2 stays as 2, 3 goes to 1, and 4 goes to 4. Right? Which is the same as wait, which one is this? Is this R composed T? So I first do T and then do R. Would that put it in the correct places? This is R cube composed T, right? Okay, so let us look at how it is related to T. If I am getting this from T by, if I first do T, I get 2, 1, 3, 4. And now if I move everything to the right by 1 instead of left, right, I get this. So this is R cubed T, right? That gives me this. This is the third one. 1, 2, 3, 4. This does 1, 2, 3, 4 goes to, now 1 and 4 are switching sides. 1, 4, and 3 and 2 are switching sides. Is that correct? 1 goes to 4, 2 goes to 3, 3 goes to 2, 4 goes to 1, right? And this you get from R squared T. Okay, if you take if you hit this if you hit T by R squared, then you're moving everything to the left by 2 or right by 2, doesn't matter whichever way, you'll get exactly this one. And the final one is this one, which is 1, 2, 3, 4, which keeps 1 and 2 same, sorry, 1 and 3 same, and switches 4 and 2. R to the 1 of T. Okay. Now, these are all my reflections. These are all the axes of reflection that I have in a square. So these are all the ones that I can get. Okay. Now recall R to the in this case, since it's a if you look at it, this is going to be a 4 permutation. So R to the 4, maybe not recall. Note. R to the 4 is equal to identity. Okay. Similarly, reflection squared T squared is going to be identity. Okay, because each reflection is its own inverse. If you reflect it twice around the same axis, you are going to get back your original thing, right? Therefore, T squared is identity. Therefore, T is actually T inverse, right? And that means R to the I OT is equal to I, right? Because all my reflections are the same. Okay, so this should not have been T. This is for any reflection. For any reflection, this is true. This is equal to identity. And so T is equal to T inverse, and R to the I squared is identity. Therefore, R to the I OT is equal to R OT inverse. R to the I composed T inverse, which we saw by rules of composition is T inverse O R inverse R to the minus I, which is, well, T inverse is just T composed R to the minus I. And since 4 to the, this thing is identity, in this case, this is T composed R to the 4 minus I. Okay. And so the group of rotational as well as reflectional symmetries, let G is equal to group of rotational and reflectional symmetries of I. D-I-O-N reflectional symmetries of P is exactly R to the I union R to the I composed T. Okay, and this is in general true for any regular unoriented what do you call non-oriented n-gon. And so order of G in this case is 8. For if I had taken a 6-gon, it would be 12. Thus, G is a permutation group on X. Notice order of G is 8. The total number of permutations of 4 is 4 factorial, which is 24. There are a lot of combinations that are permutations that are not going to show up, because whatever I do, however I rotate or reflect or anything, I can never make the vertices 1 and 3 be at the, next to each other, for example. These are not permitted for rotation or reflection of cube. Sorry, of a square. Okay. In general, for n greater than or equal to 3, the dihedral group, the dihedral group of order 2n is equal to group of symmetries of order of a non-oriented regular n-gon. Okay, and generally this is denoted d2n or sometimes dn. Okay, though general notation is this, used very infrequently, used very rarely, but some people do call them dn. We would be calling them d2n. Okay. So now we have seen what to do for planar figures, right? What about figures in 3D space? Well, they also have symmetric groups. So any geometric figure of any dimension has some symmetric group, has a symmetry group. Okay. So if your figure is not a regular surface, then your symmetry groups might just be the only thing that keeps them the same as identity. But if they're not, if they're some sort of a nice thing, then there are some special groups. For example, the 5 platonic solids in 3 dimensions are the following. First, cube. Second, the tetrahedron. Third, the octahedron. Fourth, the dodecahedron. And fifth, the icosahedron. Okay, so cube has n is equal to 8. Tetrahedron has n is equal to 4. Octahedron also has n is equal to 8. Dodecahedron has n is equal to 12. And the icosahedron is n is equal to 20. Okay, that's the number of vertices. I'm not going to draw most of them because, let's be honest, I am terrible at drawing, and that would be horrible. Okay, but these are very famous shapes. If you Google it, you would instantly get a result. Okay, example, if you look at the symmetric groups for a cube, okay, symmetry group of a cube, okay, maybe this is not a solid cube, I can see through it, great. Then the number of vertices is 8, so cardinality of x is equal to 8, where x is equal to set of vertices. Maybe I'll label them 1, 2, 3, 4, 5, 6, 7, 8. Okay. That's what I'm calling these vertices. Then every group of symmetries, every symmetry every symmetry of the cube, is going to induce a permutation of S. Induces a permutation of X, right? The other way is not true. Not every permutation of X is going to result in a group of in a symmetry, because, for example, whatever you do, again, 1 and 6 or 1 and 3 are never going to be neighbors. They hate each other. Okay, so let G is equal to the permutation group on G, which is the set of resulting permutations. Set of resulting permutations. Okay, and we'll call it the permutation group on X is equal to permutation group on X. Okay, then we want to show claim order of X is equal to 48. Okay, I'm not going to write all of these for every single group, but for the cubes it is relatively not super complicated. So let us try to see. Consider the 3 vertices. Consider the 3 vertices. In my figure, they are 4, 3, 4, and 6. 3, 4, 6. Okay. To construct F, to construct F in G, we define f of A, f of B, and f of C. Okay, so let me actually just call these A, B, and C rather than 1, 2, 2, 4, and 6, 3, 4, and 6. A, B, C, which in my figure are 3, 4, and 6. So I'll denote them with colors. Actually, this is 4, this is 3, and this is 6. Okay, so with the proof I'm using, these are let me just draw the figure. A, B, C. Okay. Great. Let us see what a permutation does. Stages. Stage 1. Stages. To do, and number of choices. Well, in the first case, pick f of A. Take the vertex A and rotate it, reflect it, whatever you want to do. You want to get it to one of these other vertices. How many choices do you have? Well, you have 8 choices. Right? So great. You have chosen the vertices. Second, pick f of B among the 3 vertices adjacent to A. To f of A. Well, if I'm picking f of B, well, f of B better be next to f of A. There are 3 vertices that are next to f of A. Whatever I do, rotation, reflection, whatever things I do, I have to make sure that A and B are connected by an edge. Every vertex is connected by 3 others, so I get to choose one of these 3 as my f of B. And in the final step, pick f of c among the two vertices among the two vertices among the two vertices connected to f of b other than f of a. Other than f of a. And I have exactly two choices for that. And so number of possibilities, therefore number of possibilities is equal to 8 times 3 times 2 is equal to 8 times 6, which is 48. Okay, and so these are my symmetric groups, and you can look at their permutations and things. Okay, now the main problem of this chapter is not just permutations, it is actually colorings. Okay, the Polya accounting wants to figure out how many ways do I have of coloring something. Okay, and so we get to colorings. A coloring of X is an assignment of colors, is an assignment of colors to each element of X, to each element of X. So in general, we'll be coloring the vertices of a square or something. Okay, so every permutation should have some coloring, and okay, and we are going to see how many colorings we can get. So example, using red and blue, red R and blue B, there are 22 to the 4, there are 2 to the 4 possible colorings of a square. 2 to the 4 is equal to 16 possible colorings of a square, right? They are as follows. Basically, for every square you have two choices. Sorry, every vertex you have two choices. Either you're coloring them red or you're coloring them blue. And just for the sake of completion, I'm going to label them. Description, number of colorings, number of colorings. And we'll start off with how many red there are, the increasing order. So 0 blues, sorry. 0 blues, all 4 are red, 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 red. There's exactly one coloring like this. 1 blue. Red, 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 plus cyclic permutation, plus rotational things. So plus cyclic permutations, which there are 4 of them. Well, when there are 2, things get slightly more interesting. Now I have red, red, blue, blue, plus cyclic perms, which there are two of them. No, there are 4 of them, I bet. There are 4 of these. But this is not the only way. I can also have red, blue, red, blue, red, blue, red, blue, and plus the cyclic permutations. These are only two, unfortunately or fortunately, whatever. Okay, because either the vertices 1 and 3 can be red, or 2 and 4. If there are 3, then now we start being in the other side of the symmetry: blue, red, blue, 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 plus symmetric permutations, so that's 4. And if all 4 are blue, 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 then I get 1 permutation, right? So there are a total 16. But as you saw, there are only 6 ways of coloring it uniquely, right? The rest of them are just cyclic permutations of this, right? So view each coloring as a function x to red or blue, where any vertex I goes to color assigned to I. Great. Now, given a permutation f in G and a coloring of C and a coloring C of X, we can permute the elements of X by F to get another permutation. Permute X to get another coloring of X, right? I can rotate them, I can reflect them, I can do whatever I want. Like, technically I can do only 2 of these things, either rotate them or reflect them or a combination of both, right? But these are the only things I can do. And by doing so, I get a new map. Composition, C composed F inverse is a coloring of X, right? So why is it C composed F inverse? Because to get from this new X to C, I would have to first go up, right? I would have to first go up, which is F inverse, and then go C, right? That is why it is C composed F inverse, and that gives me a new coloring of Fx. Define F star C as C composed F inverse. Okay. Then F star C is also a coloring of X, coloring of X. And what does this do? Which assigns to I, any vertex I, in X, the color C of F inverse of I, right? Note that now this is actually a permutation from all the set of colorings. So I'm taking a coloring and I'm getting a new coloring if I hit it with F composed star. Note, sorry, by by F using star, I'm getting a new coloring. So F induces a permutation of the set of colorings of all X, of all colorings of X. Set of all colorings of X. And what are these colorings of X? Well, how do you get a new coloring of X? Coloring of X. You start with C and you hit it by F star. Right? And that is what you get. Lemma. For any coloring C of X, for any coloring C of X, I star C is equal to C. Well, that is really easy to see, right? Because I star C is equal to C composed I inverse, which is just C composed I. And well, C composed I is C of I of something, which is literally just C, right? Lemma. Given F comma G in G, and a coloring C of X, then F star G star C is equal to FOG star C. Proof? Relatively simple, just diagram chasing or arrow chasing. What does F star G star C mean? Well, this is G star C composed F inverse, which is C composed G inverse composed F inverse. Well, composition is associative. What? So this is C composed G inverse composed F inverse. Well, I know this, G inverse composed F inverse. This is just inverse of F composed G. Well, I know this feeling also. This is literally FOG star C. Okay, and that is how we get these colorings. So lemma, given F belong to G and two colorings C1 and C2 of X, such that C2 is actually F star C1 actually, then C1 is actually F star C2. How do we show this? Proof. F inverse of C2, F inverse star C2 is equal to, oops, this should have been F inverse. I want to show that this is same as F1, so sorry, C1. So this is F inverse star F star C1. Well, from the previous exercise, this is F inverse composed F star C1. From the previous lemma, this is, no, from the definition of F inverse, this is just identity star C1, which from previous lemma is just C1. C1. Okay. So these are some of the basic lemmas that we will be needing. Okay. I will stop this lecture here. And we'll look at it in a slight bit detail more.